So I'm going to talk about algorithms for sparsely constrained optimization. I think it's a slightly lighter version of my thesis talk. I divided the talk into two parts. In the first half, I'm going to talk about the more general framework of sparsely constrained optimization, and then I take a look at the non-convex anti-constrained least squares problems as well. So the first part, I give a short introduction and talk about contrast sensing, and I then talk about the general problem formulation for sparsely constrained optimization, and then I talk about the algorithm we propose, the greedy algorithm that we propose for this optimization problem, and then we talk about the guarantees, examples, and some simulation results. So let's begin with linear models. Most of us are familiar with these linear models, where we have a vector in n-dimensional space, and we have a matrix which operates on this vector x star, and we observe some perhaps noisy version of these linear measurements, which is in an n-dimensional space, and we refer to this as y. And it has wide applications in many areas, like optics, medical imaging, economics, and so on. If the number of measurements is greater than or equal to the dimensionality of your parameter that you want to estimate, you can apply the standard least squares problem, and that is, you minimize the squared error over x. But if the dimensionality of the observation is smaller than the dimensionality of the signal, then you have a number-dependent system, and you need to apply some assumptions about the structure of x star. One of the most useful assumptions about the structure of x star is the sparsity that is used in contrast sensing and sparse linear regression. The point is that beyond this type of standard linear models, there are some interesting applications that we have nonlinearities in these models. So, for example, we have this gene selection problem, where you, for example, use a DNA marker array data, and you want to predict the few genes that contribute to a certain type of disease. As most of you are familiar with, you can apply something like logistic regression, and you can use the logistic logic which has this form to perform this feature selection or variable selection. In this particular case, the gene selection problem. Another example is in optics, which is called coherent diffractive imaging. In this application, you have a small object which usually is in nanoscale, like something like a crystal molecule or a virus or something like that. And you hit the object with the coherent X-ray beam or laser, and this object performs like an aperture, and you report the far field intensity of this diffracted field on a panel far away. And you want to reconstruct the shape of this tiny object. So what you record is something like this on this panel, the intensity of this diffracted field, and you want to reconstruct an image like this. So this is, for example, the image of a bacteria. There's some formulation where we use this form of loss function, and where the matrix L is a low-pass filter, model is a low-pass filter, F is a Fourier transform matrix, and C is the shift of the so-called generating functions, which is similar to point estimate functions in optics, which we are familiar with. And then you can minimize, you can measure the fidelity of your estimate using this objective function. And in terms of the sparsely constrained optimization, you want to find the minimizer of this subject to a number of non-derivative x being less than some known constant. Another example is the quantization, which is almost always necessary in digital communications and signal processing. So the point is that you have linear measurements, but they are quantized to a finite set, let's say y1 to yq. And then you can choose different types of quantizers. For example, you can quantize based on the phase of the linear measurements, or the magnitude of the measurements, or some combination of phase and magnitude of these measurements. Depending on the choice of the quantizer that you use, you can come up with the maximum likelihood estimation objective function. And that's another type of objective function which is different from the standard squared error. So this whole thing of sparsity function optimization started with this compressed sensing problem, where you have this standard linear model, but and you are in the high dimensional regime. There are a number of measurements is smaller than the dimensionality of your signal, but you know that there are only a few non-zero components in your vector that you want to estimate. The ideal choice for solving this estimation problem is to use the so-called L0 minimization or L0 constraint least squares problem algorithm, where the L0 norm is the size of counts the number of non-zeros in the vector that you want to estimate. So in the L0 minimization, you minimize the L0 norm of x subject to the consistency with your measurements, linear measurements, or you solve the L0 constraint least squares. You minimize the squared error subject to sparsity of x, but the L0 norm of x being less than or equal to s. The problem with these two optimization problems is that they're NP-hard, and you have to do some approximation. There are generally three ways that are proposed in the literature to study these problems or approximate these NP-hard problems. One is the convex relaxation. The second one is greedy algorithm, and the third one is the Bayesian and message passing time algorithm. I'm going to just talk about the convex relaxation and greedy algorithms in the introduction here. So for convex relaxation, we use the L1 norm, which is the best convex approximation of the L0 norm as a proxy for sparsity. So instead of solving the L0 minimization, we solve the L1 minimization. And instead of solving the L0 constraint least squares, we solve this L1 constraint least squares. For greedy algorithms, there are many greedy algorithms proposed, like orthogonal matching pursuit, recursive partial shielding, compressive sampling, matching pursuit, subspace pursuit, and so on. They have this general theme where you initialize your estimate with some at some point where usually it's at 0, and then at the first step of your iteration, you compute the residual error and update the support set of SS hat based on some rule. And this is the component that is different in different algorithms. And then based on this support set, you update the value of the non-zeros that you assume are in the estimated support set. And then you measure the error. If the error is below a threshold, then you stop. Otherwise, you repeat the iteration. So for all of these algorithms, there are some criteria needed for the measurement matrix A, or you may know it as design matrix A, to guarantee the convergence or accuracy of the algorithms. So the first one is called the coherence. So the coherence base basically measures how the columns of the matrix A are spread, in this case, how well they are spread in the n-dimensional space. And if the measurement matrix has sufficiently low coherence, then it is shown for some algorithms that the algorithm converges. The advantage of this coherence is that you can, if I give you a measurement matrix, if I give you a matrix, you can compute this coherence in a reasonable amount of time. But there's a problem with this, and that's the requirement for the number of measurements. If the signal that you want to estimate is S sparse and you are estimating in an n-dimensional space, then the number of measurements that you need is going to be in the order of S squared log n if you use this coherence for your analysis. There's another criteria that is used for proving accuracy of the algorithm, which is called the null space property. This is basically, in some way, it's a necessary and sufficient condition if you don't have the noise, and if you assume that this is necessary and sufficient condition for the convergence of the L1 or the convex methods, the methods that use the L1 or sparsity sparse estimation. So if you think of an L1 ball, and you consider your point is at X star here, and if to have a unique solution, you need that any shift of the sparse vector with a vector in the null space of the measurement matrix to be outside the L1 ball. So this null space properties in a slightly different way ensures that condition. So it means that the null space of the measurement matrix A is oriented in a way that if you shift the null space so that it passes through a sparse vector, it's not the null space is not going to, the shifted null space is not going to intersect the L1 ball in any other point. But beyond these two, there's this so-called restricted isometry property, which is more used for analysis compared to these two. And this basically means that if you apply the measurement matrix A on any sparse vector, the length of that vector is not going to shrink or stretch by much. And if you think of it for 2S sparse or 2K sparse vectors, it means that if you take any pair of K sparse vectors, the distance between these two points is going to remain almost the same under the application of this matrix A. For this, the analysis that are based on restricted isometry property require in the order of S log n over S measurements, which is an improvement over this analysis based on coherence. Now we go to the more general problem of the sparsity constraint optimization. So the problem is that we have an objective function from Rn to R, and we want to approximate the solution to this optimization problem. And this is mostly studied in high-dimensional statistical estimation. And usually, instead of estimating the accuracy of your algorithm with respect to this exact minimizer, you want to measure the accuracy with respect to the true parameter of your model. So again, you have this convex relaxation methods for approximating this optimization problem. They either solve this L1 regularization or they solve this L1 constraint form. There are some drawbacks to this L1 regularization because unlike the squared error, the case that we have the squared error here as the objective function, in general we don't know whether this type of algorithm are going to give the desired sparsity in the solution. And the other drawback is that you have tuning parameters that are mostly difficult to tune, and basically you have to use some heuristics in general. And the other drawback is that you have to assume that the objective function is convex everywhere. There are also a few 3D algorithms proposed, forward type algorithm, forward backward type algorithm, and some algorithm, an algorithm inspired by iterative hard thresholding, which generalizes the compressed sensing in the sense that you instead of assuming a linear operator on your signal, you assume a general nonlinear operator. The other algorithm is based on the orthogonal matching pursuit, which generalizes the application of this to generalized linear models. And there's also a few algorithms proposed by Beck and Eldar that are mostly from pure optimization perspective, and they use their own necessary and sufficient conditions to prove the accuracy of their algorithm, and they use the formula-wise type of algorithms. So the drawbacks of these type, some of these have drawbacks, and for example, some of them are not standalone. That is, you have to give the algorithm a vector, then the algorithm is going to sparsify that vector without increasing the objective function that much. And there are also some of them that apply to only a limited type of function. For example, this one, as I said, requires a certain type of objective function. For example, it cannot be applied to a logistic regression type of objective functions, logistic loss. And some of them require a smoothness of the objective function over the entire space. So what we propose is another gradient type algorithm, which we call it gradient support pursuit. So the algorithm requires the knowledge of the sparsity level that we want and the objective function, and it's going to output the estimate. We initialize with the zero vector. At the beginning of each iteration, we have the vector x hat, which with few non-zero entries that constitute its support set. At the first iteration, we compute the gradient of the objective function at x hat. Then we find the 2s largest entries of the gradient in magnitude, and we call that set script z. And then in the third step, we combine these two sets, the support set of x hat and the set script z, to get this set script t. And then in the fourth step, we minimize the objective function over this set script t. That is, we assume that the variable is 0 over a t complement. Then in the final step of each iteration, we turn the vector v to the best S-term approximation of it to get another SS sparse vector. And we continue this iteration until the halting condition holds. So the point is here that I have to mention, is that in the fourth step we have this minimization problem. So some of you may think that this is not guaranteed to be convex if f is not convex. But if you think about it, this only requires f to be convex over sparse subspaces, not the entire space. So the sufficient condition that we are going to use for accuracy guarantee of this algorithm ensures that this objective function is going to be convex over sparse subspaces. So what we call the sufficient condition that we are going to use is called stable restricted Hessian, which basically means that, or implies that the symmetric restriction of the Hessian matrix is going to be well conditioned. For example, if you have the Hessian matrix like this, and if you restrict the Hessian into a column, these two columns, and the corresponding two rows, the resulting submatrix is supposed to be well conditioned. As I said, it only requires, or it imposes complexity on canonical sparse subspaces. And the formal definition of this SHP, or stable restricted Hessian, is given by this. Some functions are not smooth, so we don't have the Hessians, even we don't probably have the gradient. So we wanted to generalize our results, so we wanted to our results to be applicable to non-smooth functions as well. For that, we have to use different type of tools. So for that, so non-smooth functions, you are very familiar with our type of functions that are like the hinge loss or the L1 loss. This is the absolute loss, but if you translate the multi-dimensional, you get the L1 loss. So to generalize these sufficient condition, we use this notion of restricted subgradient. So again, this is very similar to standard, or it's essentially the standard subgradient, but we only require it to exist over canonical subspace, and then we restrict the function over k-dimensional sparse or k-dimensional canonical subspaces. And we need this because if we use the standard subgradient, then it implies that your objective function is convex, and we don't want to assume that the function is convex everywhere. So with that definition, we use this equivalent of stable restricted Hessian for non-smooth function, which is called a stable restricted linearization. And then it is defined using this Bregman divergence type functions here. So now we can express the approximation guarantees for the grasp algorithm. So if we assume that the objective function satisfies the SRH of order 4s with the SRH constant mu 4s being less than or equal to this fraction, and we also have some positive epsilon such that for any lower bound of the SRH, E4s, we have this inequality. Then the ith iterate of the grasp algorithms satisfies this inequality. So we have contraction factor of 1/2 and an approximation error of in the order of epsilon. We can also get the same result if we have the non-smooth functions. If we assume that it satisfies the stable restricted linearization with constant being less than this fraction. This is slightly more stringent compared to the one that we get from SRH for smooth functions. And as I said, we get a linear rate of convergence up to an approximation error. You can relax this condition or this with these two inequalities, but then that comes at the cost of slower rate of convergence or larger contraction factor, or larger contraction factor and larger approximation error. And the other point that I have to mention about this analysis is that you can choose your reference point is to start to be any S sparse point if you're not that concerned about the approximation error. But if you want to have a reasonable approximation error, you have to choose X star to be a reasonable reference point. For example, you can assume that in the statistical estimation problem, you can assume that X star is the true parameter of your model. And then the approximation error, which depends on this gradient of f at X star through epsilon, can be related to the precision of the estimation. So one standard application of this algorithm is for variable selection. So suppose that you want to do a logistic regression, you have a logistic regression model, a logistic model, and we form this objective function, the logistic loss from m observations. The standard logistic loss has some problem because of this issue with linearly or almost linearly separable data. And if you just minimize this, you are not guaranteed to get close enough to the true parameter, because if, for example, your data is linearly separable, your solution is going to be at infinity, can tend to infinity. And that may incur a large error. So people usually use some regularization for this logistic loss. So for example, we can use the L2 regularization for logistic loss, and then our problem becomes minimizing the L2 regularized logistic loss subject to the sparsity of X. And if we want to verify the SRH for this function, for this objective function, we can apply the matrix turnoff by proved by Trop. And this theorem makes some assumptions on the vectors that you have in the matrix, in the design matrix that I listed here. So they must be bounded almost. If you apply those assumptions in our problem, it implies that the restrictions of the vector into any k indices is going to be bounded, has bounded length almost surely, and the restriction of the covariance of A is non-zero. So the consequence of this matrix turnoff for our problem is going to be something like this. If we have number of measurements greater than some constant times this R, and something in the order of k log p over k, this should be, I think this should be n. Then with probability 1 minus epsilon, we have this SRH constant smaller than 1 plus this fraction here, where theta bar is given by this expression here. And we also can apply this matrix turnoff to get a bound on the gradient of objective function at the true parameter, which is going to give us the approximation error. And if you apply this matrix turnoff, you get something of this form. So for simulation, we use some synthetic data first, and we compared the algorithm without any regularization of the objective function. And we also considered L2 regularization and debiasing at the end of each iteration. The debiasing procedure is that once you found the new sparse iterate, you minimize the objective function over the active entries of the new object, and then the result is going to be the object that you start the next iteration with. And we compared our algorithm with two convex methods, which is in the GLMnet package. The first one is a L1 regularization, which is solved by coordinate descent type of algorithm. And the second one uses the elastic net, which is the combination of L1 and L2 regularization for the same problem. And we also use another greedy algorithm, which is called the Mellon OMP, which is the generalization of orthogonal matrices to apply to generalize linear models, including the logistic loss or logistic model. And so on the left, you see the objective value, the logistic loss, without any regularization value at the estimates provided by these algorithms. As you can see, the grasp without any debiasing or regularization does not seem to converge at the beginning when the sampling ratio, the number of measurements to the dimensionality of the signal is relatively small. But it converges as the sampling ratio increases to 1. While the convex methods do not get close to the true value of the objective, the value of the objective as a true parameter, even at large sampling ratios. The interesting thing is that when you use the L2 regularization or the debiasing, the behavior of graph becomes more stable even at lower sampling ratios. So I have to say that we can compare these algorithms in two ways. One is to compare them in terms of the lower value objective, achieving lower value objective function, or we want to see if they get close to the expected risk rather than the empirical risk at the true parameter. And these are the settings that I used for generating the data. And the plot on the right also shows the same result in terms of the relative error of the estimate that we get. Again, graphs without any regularization doesn't perform quite well at the beginning. And that is partly because we are using, we don't have an exact convex optimization in that we use inside the grasp. So this sort of error can be sort of shifted a little bit to the left if we make more strict assumptions or a strict requirement for the convergence of the inner optimization in grasp. But beyond that, if you use this L2 regularization or the debiasing of the solution at the end of each iteration, you can see that the algorithm becomes more stable at the low sampling ratios, and it also converges faster than the log bit OMP to the true parameter.
So I'm not more interested in the regime where n looks like log n, like s log n or something. I mean, over here you're showing what happens when n is. I mean, it behaves well when n is growing like n by 2 or something like that. But I'm not more interested where n is.
So s,
like s log n. Maybe.
So n is fixed, right?
Yeah.
And we varied n from, I think, 50 to, n is 1,000, from 50 to 1,000 in steps of 50.
Right.
And then s is also equal to 10. So if you want to see the s,
and the entire point of compressed sensing was so that you don't have to take like linear number of measurements, you'll have to take like hopefully logarithmic number of measurements.
Right. So what you don't see here, I mean, does this not include any s log n over s log n? That one is that because we are varying m over the entire range, right? We wanted to see how fast it converges in terms of the number of measurements that we require. So what we see, for example, here is that for the algorithmic regularization and debiasing, if n is equal to around 0.4, we get into the area that is close to the true parameter. So the shaded green area is the variance of this objective function there. So I don't know how to. I don't have a plot that shows the convergence in terms of s log n, because that requires, I think, varying another variable as well. The point is that for a finite n, you don't know, you have something in the order of s log n over s, right? You don't know how large the constant is, right? So you cannot see. You have to either choose a very large n or.
So in the right, so I have a question on the right plot. In the right plot, if you have small number of samples, so your plot is blue, right? In this,
right.
And
the blue and the orange ones.
Yeah. So if you have small number of samples, then basically the n is small, and
right.
then you need to look at the left part of the plot.
Right.
In the left part of the plot, the blue
Right.
parts are actually upper.
Right. This is
Yeah,
because of this truncation that we have at the end of each iteration. Because that's not sort of a convex. I cannot say it's convex, but when you do this hard thresholding, you are not guaranteed to you are not guaranteed that your objective function value is going to remain close to what you had before this hard thresholding. But if you after you do this hard thresholding, you do this debiasing step, or you start with the L2 regularization at the beginning, even without the debiasing, then you get better result at the beginning. And if you're concerned about the difference between these two here,
Yes.
if you can you see that the relative error here is equal to 1, right? At the beginning, there's no meaningful gain. There's no meaningful difference between these algorithms because both of them, I think, produce solutions that are far from the correct solution. So we also applied the algorithm on some with the same logistic regression problem on some real data we used from the part from this NIPS 2003 variable selection challenge. We used the ARC-team data set and the Dexter data set. And if you plot the results, you see that in most cases the grasp with L2 regularization or debiasing performs the best in terms of achieving the lower loss value, except for the few cases that the logito and P performs better. And in most cases, for this data set Dexter, the grasp, even without debiasing, achieves something in the order of the results of the convex methods. Okay, so let me skip the summary and extensions because I want to talk about the Carnegie scores as well. So I want to begin this section with this caution that because some of the results might be counterintuitive in some sense. So I have to say that convex optimization is not always polynomial time, cannot be solved in polynomial time. And non-convex optimization is not always NP in general. So the problem that we want to solve or we want to address is the LP constraint least squares. We have the least squares as in compressed sensing, but the constraint here is with a non-convex LP ball, which are LP norm, which are basically are not true norms, they're just quasi-norms, and are defined using this expression here. For example, for p equal to 0, we get the standard L0 norm. In 2D, it's going to the LP ball is going to give you the axes, and for p equal between 0 and 1, we get something like this, which is a non-convex ball, and for p equal to 1, you get this diamond shape, which we are familiar with. And it is known that under certain conditions, if you can solve this, and there's no noise, then the solution to this is going to be exactly equal to the sparse parameter that you have at the beginning. Ideally, we want to say how the approximation error of this algorithm that we propose to solve this or approximate this, and the computational complexity vary by p. So to see that, first we have to see the geometry of the LP balls. So we have here 3 LP balls for p equal to 1, 2/3, and 1/2. And suppose that we have a sparse vector here, x star, and the blue line is going to be the translated null space of the measuring matrix that passes through this sparse point x star. So you can see that at p equal to 1, this translated null space pierces this L1 ball. And if you decrease p, the translated null space is going to again pierce the LP ball, but the region of intersection has shrunk. And if you further decrease P, you can see that there's no intersection between this transitive null space and the LP wall, which means that the solution for LP minimization or LP constraint squares is going to be unique. So to solve this, to approximate the LP constraint square, we are going to use this and what we call the LP projected gradient descent, which is the standard projected gradient descent for this, where f is the squared loss, and the difference is that we have this projection onto an LP wall. So for the moment, we assume that we can't project onto a non-convex LP wall. To prove accuracy guarantees of this algorithm, we use a slightly general version of the RAP, where instead of thinking the lower and upper bound of the RAP, they can be arbitrarily chosen, or they don't have any connection to each other. So the theorem that we get, or it's slightly a lighter version of the theorem that we prove, is that if you assume that you know the correct radius of the LP wall, and you choose the step size of the algorithm to be 2 over alpha 3s plus beta 3s, where alpha 3s and beta 3s are the RAP constants, asymmetrical RAP constant, then the algorithm is going to converge following this inequality, where this gamma is given by this expression, and the C, which determines the approximation error, is determined by this expression, and h of p is this function in terms of p. So this is a global convergence up to the noise level, and at a linear rate to gamma. And our result gives the first known guarantee based on R2 for the iterative shrinkage thresholding, which is the case for p equal to 1, and generalizes the result for iterative half thresholding for the entire range of p between 0 and 1. And we can also generalize this. We also generalize this result to nearly sparse x star, or what is called the compressible signals, and inexact value of r, and suboptimal choice of the step size. And the other point that I have to mention is that this gamma function and this c function, where gamma determines the contraction factor of the algorithm, and c, which determines the approximation error, are both increasing function of h of p. And if you look at h of p in terms of p itself is an increasing function of p, so then you can see that if you plot the approximation error coefficient and the contraction factor versus the contraction factor, you get some plot like this, which starts at smaller values for p equal to 0, which corresponds to the iterative half thresholding, and increases to the case for the iterative shrinkage thresholding at p equal to 1, which suggests that both approximation error and contraction factor deteriorate as you increase p from 0 to 1. So in other words, IHT, the iterative half thresholding, is the best among the algorithms for of this type of the LP-PGD algorithms. And one thing that remains is the projection onto an LP wall, which is still an open problem. So to have the LP-PGD algorithm work, we need to have an algorithm that can give us the projection onto a non-convex LP wall. For p equal to 0, we know this algorithm, which is the standard, the simple half thresholding. But for p between strictly between 0 and 1, we don't know how complex is that projection. But we have come up with some necessary conditions for the solution that I listed here, which translate into this statement here that you can uniquely determine the projection if I give you the smallest non-zero entry of the projection. That's it.
Can you give examples of functions that are only restricted convex? Like, that are not convex everywhere, but are convex only over
A
a
simple example is, I can give you a quadratic function. So suppose that you have a matrix which is 1 on diagonals, all ones, but it has, let's say, 2 on off diagonals. So it is sparse on one sparse vector. It is convex on one sparse vectors. Suppose that's the matrix. Let's call it Q, and consider the function x transpose Qx, right? For one sparse x, you are going to get x squared, or the corresponding coordinate of x. Right? That's going to be convex. But if you increase the sparsity to 2, you get a 2 by 2 submatrix of this Q. So you get 1, 2, 2, 1, and that is not convex, right? It is not positive. I can give you an example for 2 sparse as well. There's also a less simple example for general case. I think they use both quadratic examples.
So what is the future work here?
Okay, so the future work is, so for the sparsity constraint optimization, even though we can prove something with that, those sufficient conditions SHP and SRH and SRL, they might be restrictive or too strong. So I was thinking about relaxing those 2 conditions by considering convergence with respect to other metrics rather than the L2, which might be more reasonable, because in the end you want to minimize by doing minimizing the empirical risk. Your ultimate goal is to find a minimizer of the expected risk, right? So if you measure something that is more suitable with the ultimate goal of minimizing the expected risk, then, for example, if you measure the accuracy in terms of the expected risk, then you have to revise the sufficient condition in terms of that measure of accuracy. And for the LP constraint, there are also a couple of other things for the sparsity constraint optimization. But for the LP constraint, this is first there's one the open problem that whether you can solve the projection onto an LP or not. Because if you have this regularized form, instead of doing projection, you do this proximal operator. The proximal operator, I can show that you can solve it in polynomial time, right? You can solve it efficiently, even though it is non-convex. But I don't know why the projection is difficult to solve. Based on some numerical experiments, I can say it shouldn't be NP-hard, or it shouldn't be computationally feasible. But I couldn't prove it. So what I observed is that if you, as I said, if you know the smallest non-zero, you can find everything. You can find the exact projection. The point is that what I observed is that for any choice of k, where k is the sparsity of the projection, right, between 1 and n, there are at most 3 points that satisfy the necessary conditions.
So you're saying that if the constraint was in the objective, like a prox operator, then you can solve that efficiently, but you just put the constraint down that that's
not the whole LP constraint is squared.
No, the prox, I'm saying the prox operator.
Yeah, right. Yeah.
So just changing it from the objective to the constraint,
Right.
becomes hard to solve.
Right. I don't know why. When the point for the advantage of, or the point that allows us to solve that prox operator is that the objective is separable, so you can solve for each coordinate independently.
Okay.
But when you do the constraint, you don't have that benefit.
So you said like other people have studied this like sparsely constrained the general framework.
Right.
They have presumably like other conditions like
Right, so they have the most common among those results is the restricted strong convexity and restricted strong smoothness,
right.
which can be translated into be a stable restricted Hessian and stable restricted. They don't have anything for the non-smooth case, but even for the smooth case, they are sort of, you can convert one to the other.
Okay. Like they're
Yeah, I think
one.
you can convert.
Do you think they like
with,
one
with,
has
with,
the
with
other?
some subtle difference because, for example, those algorithms that use the L1 constraint method, they require the restricted strong convexity to hold over not only on the sparse vectors but also on a compact set rather than just over sparse directions. And the other thing is that some algorithms they do not prove convergence in point value. They prove convergence in function value. So they don't even use this restricted strong convexity, that sort of thing. But they also require the smoothness over the entire spectrum. That's assumptions.
Okay. Thank you.